So I created a version of the same idea that I'll show now, but in Portuguese. That's on the measurement problem. That's essentially, we can say that was this kind of the paradox that was proposed by Schrödinger. That's about the measurement and all this. We kind of don't really understand what's happened. When you have a system, we can represent the system this way. This is a quantum system, and there is a process of measurement of that system. What exactly that's happening here in this problem? There is some proposed solutions that today kind of, well, the most important. There is many word interpretation that says that the moment that you have the measurement, there is a process in which the wave kind of splits and many worlds and many universes. That's kind of puts this idea of the multiverse to answer this problem that you have here. You have also the most ancient actually the Copernican interpretation that just does this strange non-linear process that happens that's outside the description of the Schrödinger's equation. Is something that you can explain. So there is the more ancient that shut up and calculate, that ignore this strange process. There is, as you said, the many worlds, and even there is a more advanced that the people of quantum computing likes, that decoherence, that says that we can say that we kind of interpret that the quantum system as something that there is many kind of tensor products. I don't know exactly the mathematics to explain, but to what I understood that I can put here kind of tensor product, and there is a kind of scramble when the measurement, and there is these branches, and what you can say that is the macroscopic experience that you have after measurements is that you just interact with just one part of this wave. It's like the many worlds, but the branches are here. So all these ideas, all these these systems of this approach, they kind of postulate a lot of stuff to explain this. Like they actually propose infinite realities, infinite unobserved realities to explain this kind of nonlinear transition that's happened here. This is what they propose. I tend really to kind of try a critique that science, in the ambit of science itself, this is sound very strange, very non-scientific, in my opinion. That's a lack of rigor there. Almost, I can say, some that sound almost pseudo-scientific, because if you think about Occam Razor, how can you propose something infinite realities, infinite unobservable? Also, my infinite is very bad here. But infinite unobservable realities to explain. Make infinite here this way. Infinite unobservable realities to explain this transition. This is very strange. But we should look actually what is the nature of this transition. How exactly is the nature of such transition? The nature of such transition is this. We can kind of say that a quantum system is like this, and so this is the kind of the quantum system before the measurement. When you do the measurement, the quantum system changes in the way that he go to a specific some one this many parts here. There is a, as you can say, a non-linear transition. There's no linear transition that's happening, this collapse that's is something that looks like much more like a computation. The structure of this look like a computation. Non-linear, non-linear computation, this transition. This is how the structure of this looks much more. And this is this argument. The other arguments that we can say that's come from the incomplete theorem. Incompleteness theorem of Gödel. The incomplete theorem talk about, we can say that's like the traditional computers. We can call these traditional computers Turing computers. That is, so we can say here Turing computers and bigger non-Turing computers. And the Turing computers cannot have the incomplete theorem inside them. That's, they can modulate, they can do not in the same way the Hawthorne problem. But our brains, here, but our brains can modulate this. So our brains, by inference, it's some type of non-Turing computer. This is another argument that's for the incomplete theorem, that our brain is a kind of different computer. Because this is the point. The transition actually has about something about measurement, and it's about computation. Like, for example, in the case of entropy, we have the demon of Maxwell, Maxwell's demon. That's Maxwell Diamos, actually. That is about something that observed that if he had all the knowledge about the system, he could diminish, make the entropy lower. That it would be possible. So it's kind of a different observer also, that is the Laplace Deimos, actually also, that could have all previsibility about everything in classical mechanics. We can kind of talk about a quantum Deimos here. Quantum Deimos. That's what the observer is. That he have this kind of privileged position about this system. The brain in this case is the quantum Deimos that cause this, is a type of computer that cause this transition, this different type of computation. So that is here. Deixa eu ver mais uma coisa aqui. Also in my article, I know that one thing that's very problematic about to have this, essentially that the brain is kind of different quantum computer, is that how we can have this quantum effects here. Penrose, that won the Nobel Prize, he thinks about this. In the case about quantum consciousness, I do not agree with that, but just I'm using his example, his ideas, to kind of give basis to an idea to have quantum effects here. Also, birds in the system of navigation, they also probably use quantum effects, and photosynthesis also. So to have these examples, so in macroscopic and humid and more complex environments, that you could have quantum effects. It's kind of not very established, but just to give a basis to this idea here. That's the brain's this quantum Deimos that make a non-linear computation, and this is what the transition happens. This is what the transition is in this case. And as I give the critique that these models that have many worlds and others, they don't propose a good they don't have a good scientific foundation. This model, I propose a experiment. The experiment is that we have here a quantum system. Here the quantum system. And you have to kind of be aware of noise. And you have a mini brain. That is another thing. The organoid, the neuroscientists and others, they grow these organoids with neurons. So if that's the fact that you process, of course you should have kind of, it's not just randomly grow neurons, but the system of neurons that resembles actually something like neocortex. In this context I'm talking about. And this wet hardware that you have here, if it processes the quantum state with this, you induce a transition would be evidence. That is, there's some kind of process of internal process. That's this quantum dynamos. That's the applying of this Schrödinger's gate. That is the main thing. The quantum dynamos is a different type of computer, the quantum dynamos. That's this observer that has this different influence on the information of the quantum system. This quantum dynamos, that this type, that the brain is a type of quantum dynamos, apply this Schrödinger's gate. Other thing that's important in the aspect of quantum computer. In quantum computer, you have the Hadamard's gate. The Hadamard's gate, this kind of induces a superposition. You can say that the Schrödinger's gate, it's not really, because it's non-linear, it's not equal exactly, but it's kind of a Hadamard gate negated. It means that he's a quantum gate that collapses. It's not really collapse, but you understand, I'm saying this transition. So this is the brain have this inside this type of gate, and when he apply this gate to a quantum system, we have the transition. This is the resolution to the measurable problem. And one thing that's just that's about ontology. This is important. Ontology and epistemology is that we can go to the original paradox of Schrödinger. When you have here this process. In this case, the cat is the quantum dynamos, this observer that applied the Schrödinger's gate. The cat. And the cat induces the transition. There is the transition. So here you have, we can say it's not a collapse but transition, an ontological transition of the quantum system. But when the scientists open the box and finds out what happens to the cat, he have a epistemological transition. It's about knowledge. The mathematics is the same, but what is happening is actually different. This is important also, is different. So essentially this is the model to explain the measurable problem.